Before I talk to you about the fragmentation and the old-fashioned mass spectrometry, I want to talk to you about exact mass. And I have to find the darn table while I'm talking here. There it is. Okay, so first of all, the ion that you could, in theory, get if the molecule didn't fragment is called the molecular ion. And there are modern instruments that can determine this really with a high degree of precision. I'm sorry, accuracy. So this instrument is called a high resolution mass spectrometer. I don't know the current state of it because I haven't done laboratory research in probably 25 years. But at the time that I was finishing up my research, they were still a fairly rare instrument. I think that they maybe use hot, really high strength magnetics and were expensive. And so we used to send our samples out for high resolution mass spec to regional centers. So for example, there was one at UCSF, we would send it there. There was a private company near us that had one that we had one of our former group members worked at, and he would do it for us. They would do it for us, in a pinch and whatever. So when we look at a molar mass on a periodic table, we're not looking at actually the mass of a mole of atoms that are the most common isotope we work with. So for example, carbon has a carbon-12 isotope, it's got a carbon-13 isotope, it's got a carbon-14 isotope. So when we look at the periodic table and we get that mass, what we're getting is the average mass of the number of carbon-12s, the percentage of carbon-13s, the percentage of carbon-14s. It's different from the mass of exactly one carbon-12. Okay? And so what they have determined, and I'm not going to go crazy on this, but I just want to show this to you. These are the four most common atoms found in organic molecules and the most common isotope. So carbon-12 isotope was actually set. All of these are in reference to the mass of carbon-12. So carbon-12 was set to be that. And if we use that, then these are the exact masses. And if you go and compare them to the periodic table, you will see that they are a little bit different in some of the really far out, far to the right sig figs. Okay. So what's done then is you take the molecular formula and you calculate the exact mass. And by the way, these are in atomic mass units, so they're not actually grams per mole, they're like AMUs per molecule. You calculate that exact mass, and then you put it into the spectrometer, and the spectrometer can distinguish between them. And I'm there's, let me see. I want to see if I have an example here. Well, I don't have an example, but I did this in my research. It was a way of really perfectly determining, because you can get molecules that have the same I'm sorry, have the same molar mass, but different formulas. And then you can tell the difference between them by looking at the exact mass. So we're going to do some problems on that in the homework. Okay, next, I want to talk to you about isotopes. So isotopes complicate the mass spec, both in exact mass and otherwise, because if you have an isotope, it's going to slightly change. It's going to change the mass of one of these ionic molecules, right? So, for example, if we had, let's take H2O. It'll be really easy to do this, right? So H2O, right? So if we look at typical H2O, if we had 2 times 1H, right, plus 1 times oxygen 16, right? That would be, these are the most abundant isotopes, okay? Then that would be approximately 18. And the generic mass spec, the low res mass spec, only really measures to whole numbers, okay? But if we had DOH, where D, that's 2H. So we would have 1 times 1H plus 1 times 2H plus 1 times oxygen 16. That would actually have a mass of 19. And typically what we do is we call this, that's M plus, and this is M plus 1. And then if you had instead heavy water, which is DOD, so that would be, you can work it out, but that would be equal to 20, and that would be M plus 2, and so on, okay? Now, if we run a mass spectrum, because, for example, the abundance of deuterium is like 1%, what we would basically expect to see is this would have a height of, would be like 99 to 1 would be the height ratio. Okay. And so we might not even see that peak. If we really turned it up, we might see a little bump, but the problem is we get a lot of little noise in the bottom, so you can't turn it up that much. Okay. But so my favorite example for this is bromine, because bromine is super interesting. All right. Bromine is, oh God, I'm going to get it backwards. Let me see if I have it. Okay. So bromine is basically composed of those two isotopes. And the thing about it, if you look, is that the percentage ratio is like almost exactly 50-50. So what that means is that in the mass spec, if we look, if we have, if this is M plus, we're going to have a second peak of M plus 2 that's about the same height. And in fact, we're going to see a lot of this doubling even in the fragments. Because if a fragment has the bromine in it, which a lot of them won't, but if they do, we're going to see those. Okay? So there are several other examples that are important. And I'm just going to kind of give you. Okay? So sulfur Okay. Sulfur has an M plus, and let me see how I can write this. Well, it has a really common M plus 1. Okay. Chlorine is a big one. M plus is 75%, if I recall correctly. Yeah. And M plus 2 is 25%. And then I showed you bromine. M plus is 50% approximately. M plus 2 is approximately 50%. So you can see that by, if you see these kinds of ratios, sorry, it's M plus 2 for sulfur. You can kind of begin to guess if you have those atoms. The final one I want to show you is iodine. It only has an M plus of 100%, but iodine itself weighs 127 and it tends to break off. And so what we see is we see both the 127 and then we see M plus minus 127 a lot.